Okay, let's go ahead and finish up the last example problem on 8.3. And this is going to be a percent dissociation problem, and we're going to look at two different ones, a 1 molar solution, and then compare it to a 0.1 molar solution with a Ka value of 1.8 times 10 to the negative 5 on there. And again, let's just do a quick reminder that your formula for percent dissociation, and again, check to see if that is on your formula sheet or if it's something that needs to be memorized. But it is going to be the concentration of your hydronium ion over that of your weak acid, and then times 100%. So we're going to need to find the concentration of our hydronium ion that we have. So very similar to what we did in the last two examples, we're just going to, we're not looking at pH at all. We're only looking at the concentration and the Ka value. So we're going to go ahead and set this up. Now, some of you may not have acetic acid memorized. I kind of think of it as a CH3, CH3, which is kind of like your methyl, and then it's the CH on the end of it. And again, you could write that with the H out in front, but this is the most common writing of it. And I'm sure there is some logic to why they put the H at the end. But let's go ahead and just real quick do that dissociation of it. And again, it's weak. So, and I'll go ahead and write it in this order just so that you see that hydrogen out there first, but it doesn't really matter which way you write it. So we're going to start with the first one. It has a concentration of 1. And again, these have not dissociated yet, so they have no concentration. And then for every 1 molar that we lose, we gain a molar of each one of those. So we have 1 minus X, X, and X, so very similar to what we've done before, or not similar, almost identical. And then again, my hydronium ion, if you want to write it this way, or the H, I will take it either way. That should, sorry, mess that up there. That I forgot to take the X off of that, or the H off of that. So there we go. On the conjugate base there is what I was talking about. I forgot to take the H off. I don't know if you guys noticed that. And then my acid. Okay. So again, when we put our X's in, we're going to get 1.8 times 10 to the negative 5. We have our X times our X, and in this case we have 1 minus X. Again, we are at 10 to the negative 5, so using the 5% rule is acceptable on that, as is generally going to be the case here. So this is what we have. And so again, you're going to multiply and square root, and that is going to give me an X value of, and again, as always, be sure you check my numbers, 4.24, make that more readable, move it over a little bit, times 10 to the negative 3 is what I get my X to be, which again is your hydronium ion concentration. And so now we need to do our percent. Okay, let me slide this. I kind of wrote kind of big here for you, but we have our percent dissociation is going to be that hydronium ion concentration over our acid concentration, which in this case was just 1, and then times 100%. So again, put that in and run your numbers. That should just give you basically the same thing, but since we're going to do it as percent, we're going to move our decimal over 2, and so it's going to be 0.424% as a final answer. Okay? So now we're going to repeat that problem with a 0.1. Now, I don't know that there's any need to rewrite the whole thing because we know that basically all we need to do is at this point here, we're just going to change out the 1 for a 0.1. Okay, so I'm going to just 1.8 times 10 to the negative 5 equals x squared over 0.1 minus x. Now again, same as before, 5% rule is going to apply, but I would go ahead and write that in that way and then go ahead and apply your rule. Multiply over square root and x I get, so double check my numbers. Let's see, what do I get? I get 1.34 times 10 to the negative 3. And so therefore our percent dissociation is going to be 1.34 times 10 to the negative 3 over, in this case again it is 0.1 times 100%, and again finish that out and I get 1.34%. Okay, so if you have, let's just look at this, if you have a 1 molar solution, only 0.4% of it dissociates. If you have a 0.1 molar, so less concentrated, less species there, you have a 1.3% concentration. And it seems to me sometimes like that's a little bit backwards, but if you think about it, you've got less in the 0.1, so it doesn't take that many to have a higher percentage dissociate, okay, on that. And if you want to get in to the nitty gritty of it, I guess if you want to say, this is a Le Chaudière, you know, I can't say his name, a little bit of that too, because by diluting it, we're going to shift our equilibrium on there. And so again, to counteract that shift, by diluting, we're going to shift everything to the, where it has more particles. Remember that it shifts to the number of more moles, and that's the case, so it's going to shift to the left on that. So again, while the 1 molar solution has a higher total concentration of the hydrogen ions, a greater fraction of the acetic acid breaks apart in the one that is more diluted. Okay, so make sure you understand how that works. But anyway, that is a percent ionization. It's not too hard, but again, it does take what we did before with our weak acid and get your concentration there. Now, if you had a strong acid, again, it's still going to be the same formula on there, but if you think about it, if it's going to completely dissociate, then you've got 100%, right? So I mean, theoretically, you could use the same formula and run it, but you're going to get 100%. Okay, so there is percent dissociation.